Hello friends, myself Niyati Chauhan, Assistant Professor at LG Institute of Engineering and Technology, Department of Instrumentation and Control. Our subject is Distributed Control System and SCADA. In this subject, we have started chapter 3, Software Configuration. In software configuration, first we will discuss about algorithm, right? Because we are using here algorithm libraries. Okay, so first, what is the meaning of algorithms? Algorithms are connected together by software address to form a combination of functions. This is sometimes called software wiring. Okay, so these algorithms are very useful in PID, right? And we know that in DCS we are using PLC. So in PLC, PID is inbuilt. Okay, and we know that algorithms are used in analog controller, right, digital controller, and also useful in sequential controller. Okay, so next we will discuss next in algorithm library we are discussing about typical algorithm library, right? And here different types of algorithm libraries we are discussing. First, PID algorithms. So in PID algorithms, PID ratio, right? PID gap, auto and manual, supervisory control, okay? Adaptive tuning, process value versus set point error, okay? And ramp generation. These are PID algorithms. Next, input output. We are using here analog input, analog output, digital input, and digital output. Okay. Next, in algorithm library, PID functions. Okay. So PID functions mainly output limiting, output tracking, right? Feed forward, set point ramping. Okay. Then and anti-reset wind up, set point clamping. Okay, logic functions. In PID algorithms, we are also using logic functions. So, which type of logic function we are using? And or exclusive or not, right? So, this type of logics we are using in PID. Then switch, latched and unlatched. Then timer, right? Counter, okay? And sequencer, okay? So flip flop. So this type of logic functions we are using in PID algorithms, okay? And also we are using motor control, right? Next, in PID algorithms, computation, right? So we are using sum, division, mass flow, right? Function generator, high and low selector, deadline, right? Comparator, lead lag, okay? Square root, right? Exponential function and log. So this type of algorithm libraries we are using in PID. So in today's session, I will discuss one video, okay? And in this video, we have done PID tuning, right? We have installed software 5000 Allen Bradley 5000 software, and by using software we will control our process. Okay, so let's see one video.
In automation programming, we are often required to program a control loop for a given process to control temperature, pressure, flow rate, etc. This requires a target set point with a controlled feedback process variable. A PID process loop controller is designed to generate an output that causes some corrective effort to be applied to a process so as to drive a measurable process variable towards the desired setpoint value. The controller uses an actuator to affect the process and a sensor to measure the results. Often, automation technicians and programmers are required to become familiar with configuring and tuning a PID loop control instruction, and it can be one of the most overwhelming when it comes to PLC programming topics. In this lesson, we will discuss how a Rockwell Automation Control Logix 5000 PLC using the Enhanced PID Controller Function Block Instruction, PIDE. The PIDE is an Allen Bradley Logix 5000 Process Automation Controller, or PAC, family, Control Logix and Compact Logix function block that improves on the standard PID found in all their controllers. Function block programming uses diagrams with symbols to represent function and input and output connections between functions. While at first, this function block can be quite intimidating, it shares similarities of the standard PID instruction, and you'll only need to turn on parameters required by your control program. In this example, we will basically get you off the ground using the PIDE instruction and the program options essential to get it working. In case you may have forgotten what PID stands for, the P stands for proportional gain, I for integral time, and D for derivative gain. PID and PIDE are used for process control, which includes the automatic control of systems such as temperature, flow rate, pressure, and speed. The cruise control on a car is a good example of this type of control. Basically, you tell the controller how fast you want to go. The set point and the controller samples the actual speed, the process variable, and then the controller calculates an output value, the control variable, and sends that signal to the gas pedal. And just as a PID functional refresher, and using the car cruise control as an example, the P, or proportional, is described as, in the farther you are from the desired speed, the more you press the gas pedal, and on the other hand, the closer you are, the less you press on it. This works well, but when you get at the desired speed, based on this rule, you would let off the gas completely. And the end result is your car slows down and stays a little below the desired speed. Proportional control is the main ingredient of any control, but maybe a little inaccurate. For I, or integral, you wait for a little, and if there's no improvement, you push a little more on the pedal. If you are stuck below the desired speed for a long time without progress, you push the gas pedal a little further. If you still do not make it to the desired speed for some time, you again push the pedal a little further down. Once you get to the desired speed, you leave the pedal where it is. Integral control gives you accuracy, but you have to wait. And for D, or derivative, you react to sudden changes. Let's say a strong wind gust pushes your car. Suddenly your speed surges fast upward toward the desired speed. You become startled, so you release the gas pedal. As the speed surge ends and the speed stabilizes, you will then return the pedal to where it was. Derivative control manages sudden surges and may prevent overshooting your target speed. If you enjoy function block programming, as I do, you will benefit from using this enhanced version instruction over the standard PID instruction for a few reasons. The PIDE instruction offers a built-in auto-tune feature, which works reasonably well. The PIDE is programmed using a function block and not available for ladder logic programming. It uses the velocity form of the PID algorithm. This is especially useful for adaptive gains or multi-loop and cascade process control. The PIDE instruction can be switched between program and operator modes and provides full bumpless transfer into and out of cascade mode, and this instruction has more fault handling selections. The following programming steps assume the reviewer has Studio 5000 experience. Okay, let's get started and create a new Studio 5000 project. Locate the desktop or taskbar icon for Studio 5000 and launch the program. Create a new project. Select a new controller type, such as the 1756L71, and give the program a name. In this case, PIDE example. Hit Next, and in the next window, keep everything as it is, and then click Finish. For the next step, we need to create a new routine by making a new task and a new program. So first, I'll create a new scheduled task by right-clicking on the tasks and then clicking on the New Task. In the next window, I will consider PIDE control as the name for the task. The period of the task automatically becomes the sample rate of the PID loop. It is best to set it up in its own periodic task. So, I'll leave these settings without any changes, and continue to create a new program by right-clicking on the PID control task. In this menu, I'll open the Add menu and click on the New Program. I will name the program as same as the task, which is PID control. Finally, I'll click OK to close this window. The next step in the process is to create a new routine. To do that, I'll right-click on PID Control Program, then Add, and then I'll select New Routine. In this window, I will name the new routine as PIDE. Just make sure to select the type as Function Block Diagram, and then click OK. As you can see, the PIDE icon is added here, and I can open it up by double-clicking on it. Now that I've opened the PIDE program, from the Process tab in the library, I will add the PIDE function and add it to the sheet. Now, let's suppose we have a mixing tank where the temperature is to be maintained at a certain set point. The control valve allows a catalyst to be added to the tank to increase the temperature, and the temperature transmitter will send the feedback to the PID. This will represent our process and control loop for programming purposes. Now, to be able to configure this block, I need to open up the properties. To do that, I'll simply double-click on the block. In the General Configuration tab, we will use the default configuration. However, we just need to make sure that for the timing, it is using periodic mode. The control action is set to E, and for the calculate, it is using the proportional parameter, set to E, and the derivative term is set to PV. Next, in the EU's Limits tab, I will set the engineering unit scaling for both CV and PV parameters from 0 to 2500 degrees Fahrenheit, with a set point limit of 500 to 2200 degrees Fahrenheit. The control variable limits will be using the same temperature engineering units. In the Parameters tab, there are several parameters which PIDE function utilizes them, that you may or may not use them. These parameters can be manually turned off or on here. When selected, the parameter will be exposed to allow program connections. Here, there is also a description field for each parameter which gives you more information about them. I'll select the required parameters and deselect the rest. Next, I'll hit OK to save the configuration. You can see the required parameters I've selected in the PIDE block here. After the PIDE function block is configured, we can begin to add program control input and output reference tags to adjust the PIDE block performance. The main input references are the temperature PV, or process variable, which is a feedback from temperature transmitter, the SP prog or program set point, which is defined by the operator on the HMI, and the CVEU, or Control Value and Engineering Unit's output, to control the heat in the tank by opening or closing the control valve. Other inputs added are inputs for controlling the set point high and low limits, the maximum and minimum engineering units, and auto-manual control to allow for direct manual control of the catalyst control valve. The CV manual input reference value will be used for the manual control when auto-manual is turned off. The PIDE will need to be tuned, and we have to set the tuning parameters P gain to 1, I gain to 0.5, and D gain to 0 to a recommended starting point. PID tuning can be tricky, so I recommend reviewing procedures for this technique. The standard reference for PID tuning seems to be the Ziegler-Nichols tuning rules. This concludes the video, Programming Basic Control Logic's PID loop using the PIDE block instruction. I hope you've enjoyed learning what will support you in your upcoming project. If you would like to get additional training on a similar subject, please let us know in the comments.
In today's session, we have discussed about PID configuration. If you have any query regarding this topic, then you can ask me. Thank you for watching video.